Hi again, everybody. So today we next want to talk about the volume and that volume calculation that we had last time that we said, well, we can't actually take that volume. And how can I do that? And the answer was this idea that maybe there's another way to think about volume. So in particular, we want to talk about volume by shells. And so we're going to take and sort of slice this thing up into different shapes that have good volume and easy volume to calculate. And so slicing was one way to think about this. So in particular, our example that we had that was bad and couldn't work was, hey, what if we have y equals sine of x squared? And I would like to take that curve and revolve it about the y-axis. And if I wanted to do that, what we had to do before, in order to use the disk or washer method here, is I had to change my frame of thought here and think of it as a function of y. And so I had to solve my function here for x. And so I get x as the square root of inverse sine of y. And that is fine. And then I want to integrate this thing along the y-axis. Unfortunately, I can't do the integral of the inverse sine of y. And so at this point, we just don't have that tool, right? So it's just not possible to do that. So the question now is, can I change the way that I think about it and then use that to figure out the volume of this object? And so the answer is yes, I can. But the way that I want to do it is I want to think about this curve and think about the area calculation that we did, and then try to maybe work with that. And so it turns out to be pretty easy. We take our sine curve from say 0 to 1, and this is going to be the sine, or sorry, this is 0 to square root of pi over 2, so that goes up to 1 in the y value. This is the sine of x squared. Okay. And now as I revolve this about the y-axis, what I sort of think about is when I took the area of this thing, well, I took the area of this thing as being little rectangles that I was adding up those rectangles. And so what I do is I say, oh, what happens when I take one of those little rectangles that I was looking at and I revolve that around the y-axis? So what is it that actually happens here in my picture? And so that's it. So that the answer there is I get it's basically a cylinder with a cylinder drilled out of it. So it's a sort of cylindrical shape that has like a hole in it with a thickness of delta x. So it's what we would call a cylindrical shell. And so that's what we're going to use it as, is this is a cylindrical shell. And then I want to take each of those cylindrical shells, add them up, and then take the width of those cylindrical shells to 0 to integrate the thing. And that's what's going to happen. All right. So it turns out that's how it's going to work. But the biggest problem we actually have to think about is, all right, I've got this sort of nice picture here. I can't integrate that. So what is the volume of this cylindrical shell? And so I take my cylindrical shell. It's got an inside cylinder, an outside cylinder, and that's the idea. I want to kind of take that thing here. I want to know, what is the volume of this thing? Well, that's not maybe an easy question. So I guess I could take like the volume of the outside cylinder minus the volume of the inside cylinder, and there's sort of a delta x between them. Well, I don't really want to have to do that. So it turns out I can do this a little bit easier by cutting the cylinder in a straight line on one side and then unwrapping it. So I take that thing and I unwrap it, I unravel it. And what is it that I'm looking at? What I'm looking at is actually just a rectangular prism. And I can tell you some stuff. So I know that the height of this thing is given by the function that I'm looking at. The width of this thing is delta x. And now I'm just left with what's the length of this thing. Well, the length of this thing, that's kind of tricky. But what I'm going to do is I'm actually going to use like the length of this one side of this thing. It's the circumference of this circle. And since delta x is small and getting smaller and smaller, I don't have to worry about like the inside and the outside having slightly different sides or radius in that case. So what I actually get here is that this distance here is going to be the circumference of that circle. The circumference of the circle, well, that circle is sort of centered at the origin and has width or radius of x, because it's sort of out x on the y-axis. If I'm thinking about taking my curve, whatever it might be, in this case, it's like this. And I'm sort of going out to x, and then I'm revolving it. And that's the rectangle I want. Well, that x is going to be the thing that I'm going to get as the radius of that cylindrical shell. And so this is going to be the circumference of a circle. And the circumference of a circle is the diameter times pi, or twice the radius times pi. So 2 pi r is the circumference there. So this is really just 2 pi x. Okay, now putting this all together, what is it that I get? Putting this all together, I get the sum of all of these cylindrical shells and their volumes. So I get the integral from a to b of 2 pi x f of x dx. So in our example, this actually works out very nicely because in particular, I'm integrating from 0 to square root of pi over 2. I pick up an extra x in this integration, which that allows me to do a u substitution in here and get rid of that sine of x squared, just make it sine of u. And then I can go from there, and it makes it a lot easier. And so what I do here is I do a u substitution. I let u be x squared. Du is 2x dx. Solve for dx. And then I plug everything in. So I get the integral, and then I also have to change my limits of integration. So at 0, when x is 0, u is also 0, 0 squared. When x is the square root of pi over 2, u will be that squared. Square root of pi over 2 squared is just pi over 2. So my limits of integration are 0 to pi over 2. And then I have 2 pi x sine of u du over 2x, and the x's cancel and the 2's cancel. And so I'm now just integrating from 0 to pi over 2 sine of u with an extra pi out of it. And now the antiderivative of sine of u is negative cosine of u. There's a pi in front of it, evaluated between 0 and pi over 2. Cosine of pi over 2 is 0, so the first term here is 0. Cosine of 0 is 1, so it's minus negative plus pi. So the volume of this sine of x squared revolved about the y-axis is just going to be pi. Cool. So this idea of cylindrical shells is very, very nice. It comes in handy. The question we might ask now is when do I use the shells? When do I use the discs? When do I use the washers? So washers and discs, it's a little bit subtle, but basically if you have two functions, it's a washer. If one function, it's a disk. So you're sort of, if between two functions, it's just going to be a washer. Otherwise, it's a disk. And then when do I use them versus the shells? Well, that's going to be not too bad. If I have a function, if both of my functions or one of my functions are given in terms of the x value and I revolve about the x-axis, that's a disk or washer method. If I have everything in terms of x and I revolve about the y-axis, that's the shell method. Same sort of deal. If I have everything written in terms of y and I revolve about the y-axis, that's a disk or washer method. If I have everything in terms of y and I go about the x-axis, so I revolve on the x-axis, then I'm going to use the shell method. Okay, and basically it comes down to experience. So you just have to try a whole bunch of these questions and say, all right, I'm going to try it. If you get to a point where you cannot integrate, try to use one of the other methods. So sort of say, oh, maybe I need to change everything in terms of y, and then use the disk or washer method. Or maybe I need to change everything in terms of y and use the shell method. and then go from there. And so it is possible that you'll have a situation where you need to use one or the other to make the integration work out. So in particular, this sine of x squared was not going to work with a disk or washer method. It had to be done with the shell method with respect to x. Okay, cool. So that's the idea. So basically now that's volume. So what we have for volume here, we have a bunch of methods to try to do it. One of them, you're taking these cross sections, getting a cross-sectional area, bumping it out to make it a volume, and then making that sort of bump go smaller and smaller and smaller to integrate that thing to give me the exact volume. Or the disk and washer method was to say you take this sort of this rectangle, you spin it around the axis that you're interested in, that now gives me this washer, or the shell that I need. And I find the volume of that shell using the circumference and the height and and that was the delta x, the small change. I let that small change go to 0. The shells kind of get smaller and smaller and smaller, and it gets more precisely exactly the volume of the object that I'm interested in. Cool. So the homework's there. Try it out. It should be okay, I think, at this point. Let me know if you have any questions on it. Certainly, totally fine. Come by my office hours. They're all on the syllabus or whatever. Or you can actually, the Tuesday, Thursday office hour is 1 to 1:50 Mountain Time. And then the Monday, Wednesday, Friday office hour is going to be, 1:30 to 2:30 Mountain Time. So 1:30 to 2:30 Mountain Time, I'll be here, or 1 to 1:50 Mountain Time, I'll be there on Monday, Wednesday, or Friday, or sorry, Tuesday or Thursday. So Tuesday, Thursday, 1 to 1:50, Monday, Wednesday, Friday is 12:30 to 1:30, 1:30 to 2:30, 1:30 to 2:30. So I will see you all in one of those, or let me know if you have questions online. We will see how it goes. Thanks.